It's important to understand how these things work together. Now, there are many different mechanical locks. The Primus, Medico, lots of different things. They all have different approaches to mitigating some of these problems, but in general, they all have a variety of these issues. Continuing the mechanical thing, the Ving card is a mechanical punched key card. They were very popular in hotels at one point because they're very easy to rekey. Unfortunately, as you can see, they're also very easy to copy. You just sort of look at them. In fact, there was a hotel. They had a problem with a ring of thieves. The thieves would go around. They would take photos of the maid's keys, and then they would just go get a X-Acto knife, cut their own keys, and sort of go to town on the hotel. This is a real problem. Even more so, they still have the same problem as other mechanical locks, and that the lock has all the information that you need to make a key. And more than that, with these cards, because the pin tumblers inside that sort of that are actuated by the holes in the non-holes, those apply pressure that can be read by a detector. You simply have a detector card. You insert it into the key, into the lock, and you can read it. So obviously they're low security, which is why you don't really see them so much anymore. And yet they still exist in large legacy installations. In addition to electronics and mechanics, magnetism has been a boon for access control designers. Perhaps the most common is the magnetic stripe card. In lieu of a photo, I just refer all of you to your own wallets, since they are prolific. Before talking about magnetism and access control, I need to say a word about coercivity. Coercivity is just a measure of magnetic field strength. And when you're talking about magnetic piece of access control, it generally refers to how strong magnetic field you need to write to the magnet to change the thing. Now, magnetic stripe cards come in two varieties, with a third sort of pending. There's a low coercivity cards. They've been in use since the 60s. They were standardized in the 80s. They're made out of iron oxide. And there's high coercivity cards made out of barium ferrite. They've been used for quite a while, but they weren't really standardized until 2001. These things are reliable as long as there's not another magnet around. The problem with low coercivity cards is that even a high coercivity mag stripe card can corrupt the information on a low coercivity mag stripe card. So they can cause all sorts of problems there. The audit trail, though, is nice because it's electronic, so it's only limited by the back end. So you have lots of flexibility there, and they're cheap, so they're nice about that. Unfortunately, they're trivial to read, duplicate, and sometimes modify if you don't have a Mac or some other kind of confirmation on there. High coercivity cards are perhaps a little bit more difficult to write, but still, just slightly more expensive. Some people try and hide information on the cards, right? They'll try and use a non-standard location on the track. They'll try and use non-standard start or end sentinels. This is a big fan of. This is used a lot in some of the sort of automated transit solutions. But really, you can pull a magnetic reader out of a $2 tape cassette player, plug that into your sound card, and sort of wave it around on the mag stripe card, and you can read whatever they have on there. Now, there is one solution for dealing with duplicated cards. So remember, we're talking about the low coercivity and high coercivity solutions, right? These are mixtures of iron oxide or barium ferrite, and there's this sort of analog bit of that to it. And you can make a fingerprint from the grains of iron oxide that are on the magnetic stripe card, and you can make a profile for this. And the thing is that almost every card has a fairly unique sort of fingerprint of where these grains and bits of iron oxide are. There's a company called Magtech. They make a product called Magneprint, which validates cards based on this. It was, I think, used briefly by MasterCard International. I'm not sure if it was ever fully deployed, though. Prior to high coercivity mag stripe cards, you had a lot of very sort of ad hoc solutions. Every company was sort of making their own thing, and collectively these are referred to as barium ferrite cards. They preceded the HICO standard, and they typically worked by embedding a layer of barium ferrite in between some layers of plastic, or something like that. They were nice because they were very reliable, and they were high coercivity, and they were resistant to weather because they were just sort of a piece of plastic. But they were all very low resolution. They didn't have very much information on them, and so they were easy to decode. You could simply shake some iron filings on them, and you'd find the magnetized areas. They aren't really used anymore. Sometimes you'll see them in automated parking systems. That's about it. Probably my favorite, at least I think the most interesting of the magnetic access control systems is based on this stuff called weakened wire. Before talking about the actual weakened wire cards, I need to say a bit about ferromagnetism and about weakened wire itself. So this is great. So in a ferromagnetic material, when you change the polarization of one of the magnetic domains, then the domain wall moves, and you get a pulse in a coil that you can read. And weakened wire is made out of a processed magnetic alloy that's structured so that it has two almost ideal magnetic domains. It has the soft, low coercivity core that's easy to polarize, and has a high coercivity shell that's not easy to polarize since it's high coercivity. And the thing is, and so when you change the polarization of the core from the opposite direction of the shell to the same direction of the shell, then you get a nice big pulse in your sense coil. So how does this work in a weakened wire card? In a weakened wire card, you have two rows of weakened wires. You have one row representing zeros and one row representing ones. As you swipe it through the weakened wire reader, first there's a saturating permanent magnet that initializes it to a known state. And then as it moves over the read heads, two other permanent magnets switch the polarization of the core back and forth to get a nice big spike over the read coil. You can sort of see what it looks like on a card here. You can see on the magnetic film, each of those lines is one of the weakened wires. Now, these were billed for a long time as...
Whoa, someone just stole my IP address.
Or...
Whoever picked 10.0.0.222, damn you. Okay, back to our regularly scheduled presentation.
Yeah. So these were billed as really high security for quite a while, and they're actually still billed as high security if you go look on the vendors' websites. And the thing about it, at first glance, it makes sense, right? You can't walk down to a hardware store and buy a weakened wire. We can't even special order it online. It's extremely difficult to find these days. But if you'll notice, every weakened wire card has everything you need to make another weakened wire card that's different. So you can sort of cut them up and make a new one. And this attack was found in 1996. It was first published on the cypherpunks list quite a while ago. But the cards are also vulnerable to emulation-style attacks, which are another problem with magnetic magstripe cards. The basic problem is that inside of these things, right? Inside of these readers, you just have standard magnetic coils. You just have standard read coils. And so if you want to just hook a microprocessor or microcontroller up to a solenoid or a coil, you can stick that coil in the weakened wire reader, make a few pulses, and emulate a weakened wire card. The point is that you just have to copy the effect of the card rather than fabricating an entirely new card yourself. Moving on from magnetism, you have barcodes. Barcodes are great for libraries and supermarkets. Not much else. You have 1D and 2D with varying amounts of information stored on them. But they're easy, trivial to duplicate, sometimes to modify unless you've embedded a Mac in a 2D barcode or something like that. For a while, people spent a lot of time trying to figure out how to make invisible barcodes that would fluoresce when you put them under UV or infrared light. But that makes it only marginally more difficult to copy. Prox and RFID cards, they have many well-known issues. You can spoof them, you can clone them, you can surreptitiously read them. The problems have been well documented. So I'm not going to spend a lot of time talking about that here. However, prox cards are also one of the most commonly deployed systems today, right? And so they offer an interesting opportunity to look at the junction of a new system and a legacy system and some of the things that you can get from there. So about 5 years ago, MIT started deploying prox cards. Prior to that, they had been predominantly magstripe. And when they introduced the prox cards run a different system, and so they had to have different ID numbers in them. They had a different number that the central computer would validate. But the numbers between the magstripes and the RFIDs were related. It wasn't quite a one-to-one mapping, but it was really quite close. And if you give in a prox card, you can figure out a magstripe ID number, and vice versa. And this is an interesting problem because now you can sort of walk up behind somebody, surreptitiously read their prox card, and then fabricate a magstripe card. And if people aren't really looking for that kind of attack, then it can be surprisingly annoying. Proxy cards, though, they're not always that popular. People don't like being tracked all over the place. So, some people, they make their own keys. Richard Stallman, for example, his office key is a little bit special. Rather than pretending that it's him, it buzzes in as one of 5 of his office mates. So the step above proxy cards, you have CPU tokens, which is basically just a chip inside something else. Smart cards is a chip inside plastic. iButtons is a chip inside a metal can. They're nice because they can do much more complicated things than proxy cards. They can perform actual cryptographic protocols. Because the problem is that, with just a proxy card or just a standard, CPU token without any kind of protection, it's very easy to make a virtual token. You just have a microprocessor talking one wire or whatever your bus protocol is, and you sort of stick the wires to the reader and you're good to go. But these are nice because, some of them have various cryptographic things internally. But that's not to say that they're perfect. DirecTV waged a war with hackers quite a while. That lasted quite a while. The smart cards are vulnerable to all sorts of fun differential power analysis attacks and things to that effect. And they didn't actually win technologically. Eventually only won when they had the law changed in Canada. Now, Eric's going to talk a bit about knowledge-based systems.
There's really 3: mechanical combination locks, electronic keypads, and safe-type electronic locks. Mechanical combination lock you've certainly seen before. This is a Simplex Unican 1000. It looks like the white point on the projector is set a little bit low, so you can't actually see any detail in the lock. But the upshot of this system, because it's mechanical, simple to use, it's reliable, doesn't need any power. Unfortunately, it also doesn't have any kind of audit trail. You can manipulate it if you know how. It's a little complicated, but I'll teach you in just a minute. You can also use a brute force attack. Because these locks can only use one number once in the combination, you can't have a 212 as a valid combination, it just doesn't work. There's a lot smaller combination space than you might think. And a Berkeley class actually used this as an example for their students. If you go online, here's the URL. It's a nice problem in combinatorics for you math nerds. Or if you're lazy and you hate math like I do, you can just go to the second URL, which is a list of all the combinations. It'll take you about 10 minutes to run through, open every lock like this you might ever come across. But I find manipulation an awful lot more interesting because it's a lot more intelligent and a lot more cool. To understand how it works, you've got to understand how the lock works. And how it works is it has this black bar on the bottom with these L-shaped protrusions. When this bar is pushed over to the left, usually be pushed up because locks are usually mounted vertically, but here, when it's pushed over to the left, it engages these rotating tumblers. These rotating tumblers have gates cut in them, and they're rotated by you pushing the buttons. Here you can see that 2 of them, the last 2, are already in the correct position, because those last 2 numbers aren't actually used in the combination. If I were to press the 4 or the 5 buttons, it would advance those tumblers even further and cause them to block the movement of the bar. However, if I were to enter 213, which is the current combination in this lock, the first 3 tumblers would be correctly aligned and the lock would be able to open. Now, how does the lock know whether I entered 213 or 123? Every time I push a tumbler, the button to depress that tumbler is deactivated, but the tumbler is connected to a linkage so that every subsequent number I press will advance any previously pressed